Thank you very much for the invitation to present today in this ICOS City series. I'd like to start by thanking the wide range of people who have contributed to the research I'm going to present and the agencies that have funded it. There's a wide range of processes that operate together to create urban climates. These are variable across a city and distinct from their rural surroundings. The processes depend on the nature of the city and the range of activities that occur in a city. For example, depending on the economy, whether it's industrial or service-based, or the density of the population, for example, large concentrations of people in tall buildings or sprawling suburbs, or the types of transport. Each of these are going to modify the emissions of heat, water, and carbon dioxide, their quantity, source type, and location. The urban landscape is made up of a mixture of buildings, paved surfaces, vegetated surfaces, but often there are water bodies and other remnants of the original natural environment, such as outcrops of rock and bare soils. The density of buildings and their arrangement plays an important role in creating the intra-city or neighborhood climates. To model cities for numerical weather prediction or climate purposes, buildings in the model grid cells are normally described by their average height and the spacing between them. By changing the thermal and radiative properties of the buildings, the materials they are constructed from can be represented in the models. We can change, for example, the rates of heating and cooling of buildings themselves, and therefore the thermal comfort indoors that the people might experience. And then if there's poor building design, this may lead to the need to use large amounts of additional energy, which we refer to as QF or anthropogenic heat flux, to heat them in winter or cool them in the summer. With this feedback, we get potentially could get enhanced CO2 emissions, both locally and or regionally, depending on sources of energy. The amount of vegetation and the extent of water bodies will influence the partitioning of the turbulent sensible heat flux, QH, and the latent heat flux, QE. Across the city, we see a variety of neighborhoods that are characterized by a wide range of these properties. The class urban is probably one of the most diverse land cover or land use classes, for example, compared to forest types or grass types, because of the range of properties that are varying. In most cities, there is a wide range of building forms, materials, human activities, and behaviors. We often see shorter buildings in the city outskirts and taller buildings in the city center. When we draw conceptual diagrams to try and explain the flow of the atmosphere of this mix of roughness elements, so this includes buildings and vegetation, the vegetation may be taller than the buildings in the suburbs, where the buildings tend to be shorter, but in the city centre, the vegetation may be much shorter than the tallest buildings. The conceptual figure of the atmosphere identifies 4 critical layers close to the surface. The first, the urban canopy layer, this extends from the ground to the approximate height of the roughness elements. So we see that in the buildings, in the urban environment, we would call this the urban canopy layer, but we also see this over a grass surface. So here the canopy layer would be the height of the grass. I choose a grass surface because this is where most typical background climate measurements have been undertaken, for example, following the World Meteorological Organization, the WMO guidelines. Next, above the canopy layer, we have the roughness sublayer, or the RSL. This is the area above the roughness elements where we still can see the influence of the individual roughness elements impacting the atmosphere. Above the roughness sublayer, we have the inertial sublayer or constant flux layer, so the ISL or CFL. The boundary between the roughness sublayer and the inertial sublayer is sometimes referred to the blending height, because this is where we no longer see the impact of the individual roughness elements, but above that, within the inertial sublayer, we're getting the response of all those combined. It's in the inertial sublayer that the log law applies for the wind profile, and this is also where von Novikov's similarity theory almost applies. For the standard WMO measurement heights for temperature and wind, assume that the roughness elements are small, so remember this grass. So measurements at 2 meters and 10 meters above the surface are well above the canopy layer and well into the inertial sublayer, as long as the fetch is large. So for the grass surface that we have extensive grass. The other major layer is the boundary layer, which in the urban environment we call the urban boundary layer, which is going to vary by time of day and through the seasons, both due to the surface heating that's occurring, but also the background atmospheric conditions. The challenge in the urban environment is that the roughness elements are both very large and often very variable. When we undertake observations, we require to have sufficient fetch. So if we look at this image of Melbourne, what we would like to see is extensive areas that have similar fetch. So what we would like when we're using techniques such as eddy covariance and large aperture scintillometry, we require that mononomial similarity holds and the instruments are located in the inertial sublayer. Typically, we regard a neighborhood to have sufficient fetch if they are extensive. So we can see, for example, near the sea that this is the case. But if we look in the foreground, to the right, we have an industrial area, and to the center of this, we have the central business district. In the central business district, we see a whole series of tall buildings, but it's not actually very extensive relative to the height of these buildings. The depth of the roughness sublayer, so the boundary between the roughness sublayer and the inertial sublayer, is typically assumed to be about 2 to 5 times the height of the mean building height. And this depends on the packing density of the building. It's in these local scale areas that we typically model for weather and climate models. So the individual grid cells are representing a local scale area. These models are important as this is how we predict future conditions, both weather and climate. The models need to deal with this urban complexity, given we don't have sufficient observations across the city to capture it, both because of logistics and costs, amongst other things. Hence, there's a really large number of constraints on our ability to both model and observe in urban environments, and each has an influence on the surface atmosphere exchanges and therefore also on the carbon dioxide fluxes, as well as heat, moisture, and other surface atmosphere exchanges, and also are critical for our understanding of urban climate dynamics. In models, if we want to represent the buildings, we typically use their height and spacing to try and capture their key urban processes. We can simplify the materials of the surface and the human activities, for example, the variability of emissions and what they respond to. Modelers make a series of distinctions on what processes to include, at what level of complexity, what amount of variability should be simulated, how much detail should be included. For example, if we want to look at obstacle resolving models where the buildings are actually represented realistically, then we have increased computer needs. We need more information about the actual materials and characteristics of these buildings, and also typically the area that is simulated is reduced. So what we ideally need is detailed models that are two-way coupled into a larger areal extent model. So for example, if we were using large eddy simulation modeling, we would want to have it coupled into a regional model and then into a global climate model or global weather model to ensure that we're getting the correct atmospheric forcing for all of the models. As we go into modeling, even for a very simple type of model, we have a wide range of parameters that need to be set. This is challenging for cities on a global basis, even when we choose the simplest of models to be used. Land cover fractions can be obtained from Earth observation via satellites, but analysis needs to be undertaken at high spatial resolution. Even at the 12-meter resolution, the DLR Global Urban Footprint Model has problems resolving buildings from the ground in many areas, so it's distinguishing, for example, roads from buildings. Obviously, there's also the need for the data to be updated regularly, given the rates of change in urban areas, the increasing urbanization, and the increasing extent of urban areas. For example, the global IGPP dataset is missing a large fraction of Chinese cities, which are clearly evident in the GAF data. Vegetation is also important in cities. There is the issue of how phenology is dealt with in urban areas. Many of the global climate models and numerical weather prediction models use a fixed monthly climatology based on Earth observation data, but this can be poor or even missing leaf area index data for urban areas. Often this is because of a similar problem with detecting the buildings themselves because of the satellite resolution that is hard to detect the vegetation relative to the other characteristics that are present within the urban environment, such as buildings and roads. The emissions, for example, of anthropogenic heat flux are also highly variable, but often not well caught within the model. So if we take in this case here, this straight line for the anthropogenic heat flux is as used in the Marusis model within the unified model of the Met Office, that we see that there's no variability by time of day or by day of week, but even a slightly more sophisticated model shows us that that variability exists. That would change with human activities and with atmospheric conditions. In this case, the Marusis model does allow for variability, but again, dependent on the fraction of built land cover. We also need to represent hydrological conditions. If we use, often these models use separate tiles, so the built surfaces are separated from the vegetation and other types of surface types within the model until the first layer of the model. So if we're looking at urban or built surfaces, then often rainfall will be lost from the model within one time step, and they could have no external water use, so garden irrigation, street cleaning, or water used for dust suppression is not actually included. So both of these, the fast runoff processes and also the lack of external water, will impact the soil moisture, which will again modify our latent heat flux and carbon dioxide flux modeling. We also need to account for the roughness of urban areas. This may be represented by drag coefficients and/or roughness lengths and zero plane displacement heights. These typically assume that the buildings are all of the same height and use models such as the McDonald functions. So what the model is doing is typically the numerical weather prediction model, the climate model, links the surface model to the atmospheric model at the blending height, so at that boundary between the roughness sublayer and the inertial sublayer. So in the inertial sublayer, as I said before, Monodromy similarity and the log law applies, but it doesn't apply within the surface layer model. Therefore, if we apply them, we expect the wind speed to go to 0 at the height where the roughness length and displacement height occur. So this means that it's roughly just below the mean building height shown here in the grey. So here we're looking at the dots of sonic anemometer observations taken in Berlin for neutral wind conditions. The horizontal lines give us some idea of the variability of those observations under these conditions. The black lines show the monodromy similarity and log law predictions of the wind profile. So we're going down towards the surface, and that we can see that it becomes basically 0 just below the mean height of the buildings. So this is saying that there is no wind below the surface. So in this case, below the mean building height, or just below that. So in this case, sorry, I said Berlin before, but that should be Basel, sorry. Here, the average height of these buildings is 14.6 meters. So if we think of the typical WMO measurement height for wind speed of 10 meters, then that would be below the average height of these buildings. What we can see is that the observations don't fit well to the Monod-Cross similarity theory or the log law assumptions of the wind profile. And Kastner-Klein and Rotak's assumption, where they adjusted it, we can see that the wind, so using wind tunnel observations, you can see that it works, takes the wind slightly lower into the below the canopy height, but still assumes it's zero, well above the mean height of the buildings. Other models that have adapted the Monod-Cross similarity theory with the roughness sublayer correction include those of Harman and Finnegan and Derrida. We can see the red one, Harman and Finnegan, actually approximates this reasonably well under these near neutral conditions when the wind is flowing across flat roof buildings. So if we look at different flow conditions, now we're looking at different roof types, flat buildings, pitch roof buildings, and now also looking at, with observations in Gothenburg, Göteborg in Sweden, that we see that the Harman and Finnegan model actually works remarkably well for all of these different roof types, and also for different stabilities for the different columns for very unstable, and near neutral conditions. So it's performing quite well across a range of conditions. We also can look at using the same approach for determining the temperature profile. There are less options for that, but we also see that the Harman and Finnegan does a reasonably good job of simulating that. Given that, we've included the scheme, the Harman and Finnegan scheme. It's been incorporated into the SUSE land surface model. This models energy and water exchanges, but also includes urban carbon dioxide fluxes. This is work being led by Lena Jarvi's group in Helsinki, and this is ongoing development work. Although there is already a model that separates both anthropogenic and biogenic sources of CO2 fluxes within urban areas. So by putting this improvement into the model, we can not only help improve CO2 flux modeling by making realistic conditions within the urban canopy layer and the roughness sublayer, and also therefore what might be experienced by plants. But we also can use this for improving building design. So we can make certain that, for example, when architects and engineers are designing buildings, that they have more realistic weather data and profiles for doing building energy simulations, for example, shown using Energy Plus. If we make more realistic building designs, then it's likely that we can reduce CO2 emissions, because the buildings should be able to be designed to operate for longer periods using natural ventilation rather than requiring mechanical heating or cooling, which obviously require energy. In London, we've been making a wide range of full-scale observations using large aperture scintillometry, using ceilometers or ALCs, automatic lidars and ceilometers, and also infrared thermometry. The ceilometers allow us to look at variations in cloud cloudlet, but they also allow us to look at variations in mixed layer height and how it varies with season and cloud conditions. With a forward operator to forward model the attenuated backscatter observed by the ceilometer, so beta, then we can evaluate numerical weather prediction models. So on the top, we see the shading gives us the observed attenuated backscatter. The crosses are the observed mixed layer height as derived from the Kaban scheme developed by Simona Kautas, that we can then use. In this case, we're using the UKV, which is the UK Met Office's regular weather forecast. This is at 1.5 kilometre resolution on a horizontal scale, and the blocky nature. If we compare then the modelled attenuated backscatter, we can see that there's clearly a big difference in mixed layer height. If we compare the two of those, we can see, so we separate these, we would subtract them, would ideally see a white, but we can see that there's a large difference. We can see that this is because the mixed layer height on the model is not actually deep enough, and therefore that the mean concentration is close to the surface. So shown here for aerosol, relative humidity and air temperature, but also would impact CO2 is much. So because the boundary layer is too low, the concentrations are too high close to the surface, and therefore the models is not performing correctly. So what we need to do is to improve the urban land surface model. So what the Met Office has done is replace the best one-tile scheme with the Marusa scheme. We can see that the black line is the observations of turbulent sensible heat flux, that we can see that they're getting the timing of the sensible heat flux better using the new model scheme, and we also improve the aerosol concentrations close to the surface. So looking at the operational weather forecast model, so this is on the left with the old scheme and on the right with the new urban scheme, we can see that the timing of the mixed layer height growth is improved by the improvement of the scheme, and that we also get better performance in terms of the concentrations, although there's still opportunities to improve the model. We're currently undertaking observations in Berlin as part of the Herbosphere Project. This is being led by Andreas Christian and Daniel Fenner both from Freiburg. This includes a network of scintillometers, Doppler lidars, and other instruments, including scintillometers and infrared thermometry. And later on this year, the Herbosphere measurements will move to Paris, where there's obviously a lot of CO2 research going on. Again, the work in Paris will be led by Andreas Christian, and the lead PDRA will be Will Morrison. The depth of the roughness sublayer, and therefore if an inertial sublayer exists or not, we influenced by the presence of tall building. So up to now, I've been sort of focusing on relatively idealized situations. But as soon as we start to allow for some of this variability within the surface, even our simple models that we're still trying to improve have challenges that we need to consider. So what we typically assume in the models is more sophisticated than these cubes shown here. We can see that we can get some idea of the variability of the surface temperature taken here with infrared thermometry. We can see that there's large variability over these cubes, even though that they're all basically identical and that they have very simple geometry. This is much simpler than reality, shown here for London, much more complicated modeling environment, a much wider range of surface temperatures being modeled with variations in materials and orientations, amongst other things. And that is challenging. One of the ways that we can actually start to explore wind flow variations and the impact of individual tall buildings, which are very hard to observe in the real world, is to use wind tunnels. We can put into the wind tunnel somewhat realistic hardware models of parts of the city and start to explore the flow around them. I'm going to focus primarily on the wake, so what happens behind the individual buildings, and start to look at the impact first of just isolated tall buildings. So the area I'm showing you here is for an area south of the River Thames in London. The buildings, the models, so you can see photos of them here and a sort of a cartoon above, have no actual details. So they're just flat surfaces, but we have the general shapes correct. The overall locations are correct also. In this study, we focus on two tall buildings, one that is 81 meters tall and one that is 134 meters tall. The 134 meter tall one is approximately triangular. So when we're looking here, because the model is sitting on a turntable, basically we can move the buildings around and put the buildings so that they're upwind, and then we can look at what happens in terms of the flow as they come over the building. So we're going to look at sort of what happens. So the flow is coming in this direction, and what happens behind these buildings. What's the impact of just adding one individual tall building to this area? So to do that, this is sort of the beauty of the wind tunnel, is that we can remove individual tall buildings. So in the first case, we have the core with the tall buildings here present. We can take the tall buildings out, or we can take all the buildings away and just leave the tall buildings. So we can look and see what the impact of that is. These individual dots then show where observations have been taken. So this model is a 1 to 200 scale model. The observations are taken with Doppler anemometry, and that we can take the measurements in a variety of different locations. We can do profiles behind the building. So in this wind tunnel, which is one of the largest wind tunnels in Europe, it is wind tunnels 1.5 meters high and 3.5 meters wide. But because the LDA is moving around on the top of the wind tunnel, we can't get much higher than the height of that tallest building. And we're also the flow is starting to be impacted by that, by the ceiling once we get close to that, much higher than the tall building. So first, we want to explore the impact of looking at what happens if there are no tall buildings present. So the dots here show where observations were taken. The black line here is the log law, and the grey squares are the observations. So what we can see is that once we go high above the surface, without any of the tall buildings present, we're sort of starting to fit the log law well. As we come closer and closer to the surface, that we see that we're not fitting the log law as well, but we can see that we are measuring wind even quite close to the surface, and that this sort of yellowy shading, this is the height of the roughness, length and displacement height without the tall buildings present. When we add this individual tall building, we can see that the roughness, length and displacement height becomes slightly larger. So once we add the tall building in, we're looking at measurements that are within half the height of the tall building. We can see that there's a massive change in the wind profile. As we go out to 1 times the height, and now we're taking all of the measurements within that area, going further out 1.5 heights of the building, 2.5 times, and then looking at all of the observations, so all of the measurements within that, we can see that we still have not actually returned to the same wind profile as that we had before the tall building was placed within the area. We also can do something similar for the 134 meter building, and we can see that even going out much further to 4 times the height of the roughness elements, that we still have not actually returned to the perturbation is still impacting the wind profile significantly. We can also see that the impact extends way above the height of the tall building. In the UK, a commonly used air pollution model is ADMS, and part of this is ADMS build that allows it to model the wind flow behind the main wake of an isolated tall building. we can use the wind tunnel observations to actually evaluate the performance of this. So we're looking at how well does this model predict wind velocity. So we're considering transport relative to the center line of the tall building. So the color, so we look here, gives you a sense of how far away is the measurements from the center line of the tall building, which is what's being predicted. So ideally, it would fall on the one-to-one line, the solid line here. That what we can see is that we're also showing what fraction of the data are within plus or minus 10% of the reference wind speed. We can see that that is still close, higher up, we're getting good performance, but as we go closer and closer to the surface, that's closer, that those performing less well. For the shorter building of 81 meters, there's greater than 95% of the data are represented within plus or minus 10% within 2 times the height of the tall building. But for the taller building, 134 meter building, that's even at 4 times the height of the building, we're still just getting to that point. So what we can conclude is that the ADMS model is able to predict the flow for the slender, shorter, isolated tall building better than it is able to predict for the wider, taller, non-cuboid building. The better prediction of the flow occurs further away from the tall building and vertically further from the surface. So the flow is being perturbed both horizontally and vertically. And if we're trying to actually understand carbon dioxide emissions and the transport from sources, it's really critical that we understand not only the average conditions, but also what the impact of individual tall buildings will be in an area. It's very, very rare that all buildings are absolutely identical height. Some of this work is work that we're developing now in 2 projects, the NERC Ashore project and the EPSRC Future project. These will involve undertaking, but these results also have impacts for undertaking observations that we need to be thinking about individual tall building and what the impact of those are to the flows. Now I want to turn from looking at an isolated tall building to a cluster of tall buildings. So in many areas, such as in Asia or South America, we would see clusters of tall buildings. So similar to a wind tunnel, we can also use water tunnels. So what we use within this is a 3D printed model. This allows the buildings to have more realistic details, but still to be simplified compared to reality. In this case, we're looking at a cluster of tall buildings in an area of Beijing, representing just an area just north of the IAP tall tower. Again, we can build a series of tall models and we can rotate them for different wind directions. We can also print the model at different scales. So in London, we were looking at isolated tall buildings at the scale of 1 to 200, and now we're looking at scales of 1 to 2,400 or 4,800. Again, we can take the tall building cluster out and have a baseline of which we can look at the impact. So in front of the model, we can have a log law wind profile. We can inject a dye in front of the model so we can look at the behavior of scalar. We're using particle infrared image velocity, PIV, and cliff measurements, which involve taking very rapid measurements with cameras from outside. That does actually present a constraint because it means that we can't see all aspects of the model because we're looking through the chamber and into the model. We can see a laser light, so laser sheet, so we can see the sort of line where we're actually going to be looking at. So starting to look at some results here. On the left, we have the 1 to 2,400 model. And on the right, 1 to 4800 model, we're just looking first at the case where just the tall buildings are present. So this is the same model, but at 2 different scales. This vertical line on the right shows us basically the outflow condition of the 2400 scale model. So what we're comparing here is the flow relative to the incoming log law profile, and we can start to see the perturbation. So if we look behind the building, so these are scaled relative to the height of the maximum building within each model. So the buildings are actually slightly varying height, with sort of one slightly taller building as occurs in reality. So they scale to the relative maximum height of the 2 models, and then both in terms of the x dimension as well as the z or height dimension. We can see then behind the cluster of tall buildings that there is actually negative flow. So we can see in the wake zone that there is a recirculation zone, and that occurs in both models. So these top 2 figures are the set that we were just having a look at. And we can start to look at then the variations in a whole series of different characteristics of the flow. The velocity variance, you can see as it increases as it goes across the tall building cluster, the Reynolds shear stress. From the dye, which is being released in front of the tall buildings, we can see this increased concentration in front of the tall buildings and then being lofted over the buildings. The concentration variance, the scalar flux, and also the effective scalar flux. We also then can take sort of sections, horizontal sections, and start to look at the mean profile. So similar to what we were modeling before, we're looking at in terms of profiles for wind at particular locations. So we can look close to the building and then moving beyond that, we can see that between the 2 scale models that we're getting pretty similar results. Because the measurements are dependent on the pixel resolution, obviously the pixels take up a larger area for the smaller 1 to 4800 scale model, so we see more variability. In the models, we're also seeing that there are points where we get too close to the surface and we can't pick up the details of the individual variables being observed. We can also investigate the dispersion of this ground level source, so that it's being released at the surface. So it's being released here, but now we can look at what the difference is with no buildings, just having the low buildings, or having both the tall and low buildings present. We can see that there are differences as we go through across this X dimension, and that we can see that there's been significant lofting of the dye or the scalar flux above the surface by the presence of these buildings. One of the models that's commonly used for air pollution modeling is something like Gaussian plume model to look at the dispersion. That we can see that in front of the buildings that the Gaussian plume model can actually work reasonably well. But as we go past the buildings, that a simple Gaussian plume model does not work well unless you actually lift the apparent source. So you actually have to say, instead of the source being close to the surface, that it needs to be higher above the surface before you can actually use a Gaussian plume model to actually calculate the dispersion. This cluster of buildings can also be used for evaluating large eddy simulation models. So here we're looking at using the Udales model, which is run by Martin van Rooijk's group at Imperial College London, and they're also undertaking a lot of developments for urban areas. So we're using, again, the observations in the water tunnel. Now the scaling is, instead of the maximum building height, it's using the boundary layer depth to allow the scaling between the two. So here we see one of the constraints of the observations. So the observations, we're looking from outside the water tunnel, but modeling in the center of it. Well, the model for the Eles modeling is for the same center line, but obviously we don't need to have the same buildings in front. So you can see the difference, that we're seeing more of these white blocks where the buildings are in the water tunnel observations than what we see within the large eddy simulation. We also therefore can see more detail about what's happening behind individual buildings between the two, but we can see that there is generally similar relationship between each of those variables in terms of that the shape is generally similar between the two. And again, we can look at profiles at different distances along the X dimension. Now the observations from in the water tunnel have greater variability than the LES simulations because of the greater uncertainty because of the pixel resolution. But we can see that there is good correlation between this. Obviously, the large eddy simulation can go all the way to the surface, whereas the water tunnel models is constrained by what can actually be seen of the flow. The large eddy simulation also can be started to look at what is the variations and concentrations between different levels. So here we're looking at isosurfaces from the point where the dye is being emitted, and that we can see then the higher concentration closer to the surface, and then as we go further away from the surface, that we see lower concentration. So this is an example of the 10 to the -3, so an order of magnitude smaller than the one above. This obviously is a very useful tool for starting to think about how observations or release points may be influenced by roughness elements, what the impact might be for individual sources, and where we might be likely to observe them. So we need to understand the impacts of physical meteorology to improve both observations and modeling as we obtain acceptable simple models. So I showed, for example, trying to improve the model at the inertial sublayer and determining the profile within to the roughness sublayer and the canopy layer. We can start to address more complex situations, for example, changing atmospheric conditions, changing building morphology and materials, and allowing for more human activities to be accounted for. So basically removing the assumptions now that we often make of everything being homogeneous within a grid. We need a range of models for a wide range of purposes. For example, we would like to improve our ability to model weather and climate. By doing that, we can improve, for example, building design, and therefore reduce unnecessary energy use, and therefore hopefully reduce CO2 emissions. But we also can use these models to use such models to help us improve the modeling of CO2 fluxes in urban areas, and also to understand our measurements better, or think about where we would be prepared to take the next set of measurements, or what the new challenges will be. Thank you.
Thank you, Sue, for this excellent presentation. So let's see if we have any questions. So I can ask one. If we lived in a perfect world, what would your sort of needs, what would they be? What would you wish for from the city planners regarding your work?
Oh, very challenging question. I think the critical part from city planners is probably participating in a conversation about what their needs are. So from a sort of a meteorologist perspective is how can we make things better? I mean, in the sense of, for very good reasons, we have to make weather forecast models and climate models simple. There's no point having the perfect weather forecast model, but months after the weather prediction is needed. At the moment, in weather and climate prediction models, we very rarely treat cities realistically. What we need to discuss with planners is what is really needed, what would be the sort of first order benefit, and then what is the second order benefit. I mean, and that is a two-way conversation. It can't just be sort of done one way, and that means we need to educate the forecasters as well as the weather forecasters and the climate projection people. So I think it's sort of participating in the two-way conversation, which I think is definitely starting to happen, but it requires sort of us having a meeting together. So, I mean, meeting of the ways, understanding each other's language, each other's needs, and sort of communicating in both directions. I think that way then we can hope to make sort of better improvements about where sources are, where the models can facilitate things, where observations are really needed.
Okay, good answer. We have Andreas Christen who has his hand up. Go on.
Yes, thank you first for the talk. You showed quite nicely how the airflow is affected by the presence of buildings and cities at all scales. But your view is mostly how do certain buildings affect the airflow downwind? And from the ICOS perspective, we are often interested in the reverse. So we have a sensor that is somewhere, and I would like to know whether this surface is affected by a tall building, or do I actually need to consider the tall building at all? Maybe I'm too far out of the city on a 200-meter tower, and it's more relevant to study or to implement in my model the integral effects of the city. So I would like to phrase my questions in the reverse. Are there any models that allow me to distinguish or rank the relative influence of different scales on a measurement? So if I have a measurement location, instead of looking at the dispersion, and how can I actually, or could you tell me by reversing the argument, how much is that particular location be affected by a single individual building, or by the presence of a city with anthropogenic heat and so on? I think that's still something that we have no tools for that, but maybe you have ideas how to address this in this project.
Now, I would hope that the tools that I've shown, for example, if we say that the model is, so from these observations and modeling, we can say, okay, this LES model is working reasonably well. In this particular example, we've shown an emission point at close to the surface, but we could obviously now make emission points at a whole variety of different places to actually address this question. So I think it's absolutely critical that and most the sort of high resolution influence of individual tall buildings and the modeling for either wind tunnel, water tunnel, or LES type modeling is exactly allow us to look at exactly those issues of what if you were to, I've just shown one point source, but the point source could be any technically could be anywhere. It could be close to the surface, it could be high above the surface, and so that you can actually start to look at what the source area is. So you can actually say, okay, if I'm measuring at a particular point, what is the implication of that in terms of the emissions? So I very much, the intention here was to actually try and address those and that. So when I say that this modeling can help us think about observation, it is exactly that, about thinking about where have the observations, what has been observed, what is the source of what is being observed, and that rather than in the sort of simpler source area models, now we're taking into account the tall roughness elements that could be at lots of different orientations.
Thank you.
And we have a couple of questions in the chat. We have one question from Lucas. He asks, what are your thoughts on using LES models at city scale as done, for example, in the Palm4U project? In your opinion, is this the next step for meteorological modeling in cities, or would you rather see further developments in mesoscale, approximately 10 to 1 kilometer models?
So the next generation of weather forecasting, operational weather forecast modeling, will be of the order of 100-meter grid. So high resolution weather forecasting, for example, is of the order of 1 kilometer today. As we go to LES modeling, where buildings are being resolved, those models at the moment, Palm4U is doing a really fantastic job of trying to deal with this nature of variability, and so for answering questions such as where are the sources of emissions and what are the implications of the roughness elements, they're very important. The challenge for weather forecasting is that you've got to do the weather forecast in advance, and you've got to make certain that you're providing all the appropriate detail and that the computer resources are available. So we can make more complex models. For example, you see very on the screen at the moment, very complex urban form, but we haven't got all the building materials being realistically accounted for, etc. What you've got to decide is, if you have a nested LES model and there's an area of concern, let's say we're about to have an air quality episode, or a situation where you're interested in sort of resolving a particular, say, CO2 emission situation, then you may be very interested in two-way coupling modeling system. What you've got to make certain is that the additional computer resources are going to be able to provide the appropriate model outputs, because the challenge is, do you want one very detailed model, or do you want an ensemble of quote unquote less good models, but that you've got a number of different states that you could be looking at, and that you would like to look at the range of possibilities? So that's not, LES is very helpful for looking at certain cases in detail, for improving our understanding. But you're not going to be doing LES modeling for all cities globally in the near future. And that if you want to look at cities more generally globally, then you're likely to go more towards the ensembles route. So doing a number of models with slightly different states, either just a perturbation in the meteorology, or looking at different characteristics of assumptions within the model to try and get better information. I think with all of these things, there isn't one answer solves everything. It's a matter of a synergy between these different modeling approaches and assumptions, so that we can improve our understanding of the aspects that we're simplifying at the moment.
Okay, thank you for this answer. Then we have another question from Zeng. And the question is that, is it possible to measure anthropogenic heat? Thank you.
So by So we've done yes and no. The yes is for individual buildings. For example, Symons published a paper on atmospheric environment in 2012 that we're using eddy covariance, we could actually detect the anthropogenic heat and also CO2 emissions, but that's effectively at the micro scale. To measure across all of the, sort of at the neighborhood scale, that is challenging because of the nature of the variability, and that's there are observations done by difference, basically saying, can you measure all of the components and then assume then that you've got the anthropogenic heat flux? You can, with eddy covariance at the neighborhood scale, you can get the sensible latent heat fluxes reasonably well if the sensors are well located, or large aperture scintillometry. You can make a set of assumptions and determine, for example, this by so Ben Crawford in the Quarterly Journal of Royal Met Society, I think published in 2017, demonstrates sort of getting a measurement of anthropogenic heat flux, but these are starting to be averaged in each case over quite long time periods. They're not instantaneous measurements of the fluxes like what you would get from an eddy covariance sensor or a radiation sensor or something like that. So they're sort of, you're aggregating in time to get that. There's also been work by various people, including Nick Christoulakis at Forth in Scientific Reports, I think published in 2018, that use remote sensing techniques, but others have also had goes at it. But none of these are direct measurements of anthropogenic heat fluxes. They're all requiring sort of some time averaging. So I think at the moment it's still quite challenging to measure.
Okay, thank you. I think we can still take one question from the chat. I think our time is running out. So Marcel has a question, a technical question. Is it possible to specify the flow in urban areas by a Reynolds number? What is the Reynolds number for a flow in urban areas?
Okay, so obviously the stability is changing, and you would also want to know, where you actually are. So yes, there are, I mean, all of these models have Reynolds numbers. You're trying to get into turbulent flow for actually using, for undertaking the modeling. So, there are values. Is there one value for all of urban areas? No. But I mean, I'm happy to provide, series of papers where values are being values are given, and there's sort of a variety of in terms of thinking about what would be appropriate values for scaling of urban areas. There's been a lot of work thinking about those.